Cool.
studio.azureml.net. Not the most snappy. Yeah, there you go.
Yeah, cool. So what are we doing?
So we're going to start with using one of the pre-built-in data sets. So we're going to get an idea for what machine learning is and how it works at the beginning, and sort of see if we can solve a problem using one of the pre-built data sets. So it's a bit artificial, but it's a good start.
Yeah. What problem are we trying to solve in the beginning?
Yeah, so there's a bunch of flights in the US, and we're going to take a whole bunch of data on the arrival times of those flights, whether they came in early or late.
Yep.
And a whole bunch of other data about the flights, and see if we can predict whether a flight will be late or. So machine learning is comes in sort of two flavors. You've got unsupervised learning and supervised learning. Right. So unsupervised learning is more about exploration and looking for patterns in data.
Mm-hmm.
Supervised learning is where you know the answer for a bunch of data to begin with, and then you're using that to try and predict the answer for data where you don't have in the future, right?
It's kind of like trying to find the next number in a sequence.
Yeah, it's about trying to make a prediction. Whereas unsupervised learning is more about looking for patterns and trends and things like that.
Yeah.
So supervised learning requires you to have what's called a labeled data set. So it requires you to have one value, one variable in your data set for your training data where you already have the answers. And then what you do is you fit a model using all the other variables in your data set to see if you can best predict what that answer is. And it tunes itself to try and best match those answers in the training data set.
Yep.
And then you hit it with a set of new data that it's never seen before, and it actually tries to predict that value in that new data.
Yeah, okay, cool.
So in this case here, our training data is going to be data on the flights, where we actually know how late they came in, or in some cases came in early, and then we're going to give it a bunch of data without knowing whether it comes in late or early, and see what it predicts the flight will be.
Cool. Okay.
Cool. So the other thing, there's a few different types of predictions that you can make too, but the main, but you'll often hear about classification and regression as sort of the two main things. So classification is putting things into a bucket. Often it's a yes, no, true, false, whatever.
Mm-hmm.
But you can have multi-levels of classification. And regression is about trying to predict a value.
Okay.
So let's make a call here. Would we like to try and predict what value, how many minutes late the flight comes in, or would we like to say whether the flight will be late or early?
I think let's go for the simpler one, which I presume is it going to be late or early?
One isn't necessarily simpler than the other.
Oh, right. Okay. Well, it doesn't matter then.
Well, let's start with trying to predict the actual value. Let's look at the regression problem, and then we can talk about classification, maybe another session.
Mm-hmm.
So that's a regression problem. So it's called a regression problem because it comes from the world of statistics where regression lines are fitting trend lines.
Yeah.
Cool. All right. So if we go into an experiment. So this is a visual way of doing this stuff, and it's a good starting point, I think, for exploring machine learning problems. So if you go down the bottom, hit new.
Slow down there. New.
We'll just go blank experiment.
Blank experiment. Right.
So it's a drag and drop interface where you can put all sorts of things in. Let's grab the data to begin with. So save data sets, or you can search in that search bar, flight. There you go. So you've got flight delays data. Let's use that one.
That one? And you want me to drag that in where the database pictures? Yeah. Okay. So we're starting off by firstly saying, hey, we have some data in a structured way, and that's our starting point.
Correct.
Right.
So in some cases, this is actually a luxury. So you might not actually have data in a structured way to begin with. So if you right mouse button on the node at the bottom there and go to visualize. Visualize. It'll bring up a table, right? So this is actually to some extent what you're looking to get to before you can do a machine learning problem. So think of it like a database table, basically, right? Columns and rows. Each row is an observation. Each column is a variable. And in machine learning, they're often called features because I don't know, people like to invent new words for things, but they're often referred to as features. So features are the ones that you can use to try and predict things. In statistics, often called predictors. And the label is the thing you're trying to predict. So we've got things on the date, year, month, and day of the week, the carrier, the IDs of the airports. If you scroll to the right, so we've got 14 different columns in this. And the one we're looking for is that final, or not that final column. Oh, it is. No, it's not. ARR delay, so arrival delay. That's what we're going to try and target.
Yep.
So that's how many minutes late the flight is.
Yeah.
So you can see.
So a negative number means you came in early, and a positive number is it's late.
The other option, if we're doing classification, is to target the next column across, the arrival delay 15. That's flights that came in more than 15 minutes late, and you could start trying to classify to see whether it's a true or a false, and whether it came in more than 15 minutes late or not. And that would be a classification problem, putting the flights into the buckets.
Yeah. And that's more of a binary value, isn't
it? It doesn't necessarily have to be binary. You can have multiple classification categories. So you could have, in the flights case, you could have early, between 0 and 15 minutes late. They don't even necessarily need to be ordinal. They could be, is it red, white, and green? It's not like red is greater than green or anything like that.
Okay.
So, those are different options.
Yep. So we have all of this data, and we're going to use that to predict for a certain flight whether it's likely to be early and late, or late, and by how much.
Yeah. And so what you're looking to do is to get the data into a form that looks along these lines. Now, this still needs some cleansing, but you're looking to get a table of data. You're looking to get features and observations.
Yeah. So just, in layman's terms, an observation is a record, and a feature is a value or property on that record.
Correct.
Right. Okay.
Yeah, cool. Exactly. So, you look to get in that form. So to get it to that point, you might need to pull from lots of different sources, do a whole bunch of joins. You might need to search through unstructured data and extract appropriate information. There's a whole bunch of things you might need to do to get to this point.
Okay.
And even once you've got to this point, there's still going to need to be some work we're going to need to do on it. But to take the example we were talking about earlier, you need to look at information on the particular. Do you want to talk about this or not? Yeah, information on the particular stocks and information on the records from media and all that sort of stuff, and try to arrange it in this sort of format. So a lot of the heavy lifting is actually done
before it gets to this point.
Yeah.
Just getting it into a format that you can work with.
Yeah. So when they say machine learning is 80% data preparation, that's what.
Yeah, makes sense now. Okay.
Okay, so I've got a version on my screen too where I've actually done some of this before. So what we're actually going to do is we're going to do a little bit of preparation on this beforehand. So often when you get data in, there's crap, for want of a better word, in there. There's some cleaning to do. So you don't necessarily want duplicate rows. If there are deliberate duplicates in there, that's perhaps an error in how the data's been collected or accounted for and stuff like that. So one of the first things you do is look for duplications, and where that is a true duplication, kill them.
Yeah.
Now you might end up with duplicate rows that aren't actual duplicate records, but if that's the case, there needs to be a reason for it, if you know what I mean.
Yeah.
And it's probably because you're missing a column.
Which is some identifier.
Yeah, so a true double recording of something you don't want. But if, two flights with the same number arrived at the same time late, that might be because you haven't got the date included or something like that. Because the flights often have the same numbers on different dates and things like that. So anyway, so here we want to remove duplicate rows. So one of the first things you'll do is look for the block that removes duplicate rows. So clear the search.
So I just look back there. Oh no, that's not it. Right.
And then there's a whole bunch of things that you can also just search for duplicate.
Right.
remove duplicates or duplicate or something.
Data transformation.
That's
so
it.
I'm going to drag that and put that
underneath. And
somewhere
then
there.
the great thing about this tool is it sort of becomes a visual flow, right?
Yeah. And then I'm going to drag from there to there.
Yeah. So now if you look at the remove duplicate rows, you'll need to select some parameters on what it defines as a duplicate. So if you go over to the right here, launch column, select that, and you need to tell it what it's defining duplicates on.
So I would think that year, month, day of month would all be identifiers.
Yep.
Yeah. Those three. Move those across.
Yep.
And what else? Origin, destination.
Yep. Carrier.
To
be honest, it's probably all.
Yeah. Okay. So let's just select all of them and move them across. Yep. And then hit the tick. Yep. Are there any rules?
You can build out sort of more complex rules on how to select columns and stuff, but in this case, it's just the rule is everything. So.
Righto.
So if you go back to the visualize on the data output.
R1.
Yeah. So right that's button. Oh yeah, if you need to grab the node. You can see 2.7 million rows. Top left corner.
Oh, right. Yep.
So if we now look at the output and visualize the output of the remove duplicate.
Okay, so we're using a count.
Actually, it won't work yet. You need to hit play, down the bottom. Run. So this will actually execute there.
But it doesn't fundamentally change the source data, right? So where's that deduplicated data actually held?
The original data?
No, the output of remove duplicate rows.
Yeah, it'll be in memory.
Okay.
So it depends. This is an interesting question to some extent because in big data you need to start being careful with how many versions of the data you've got in existence because actually keeping the data around can be costly and take up lots of memory and stuff like that if it gets really large. So you might actually change the data and if you want to go back to the original, have to re-extract it from the data sources or something like that.
Okay.
In this case, even 2.7 million rows is not really that much.
Okay.
So you can afford to have multiple versions of the data in different formats in your memory. It's not going to be a big deal if you've got enough memory.
So I'm assuming I got visualize this, and that should give us a.
So you should get a reduced number.
Yeah. So we got it looks like the same 2.7 ish. So that's 2719418. Okay. 2719418. Yeah. So it's the same. So it's likely that there are no duplicates in that data. I'm not going to scroll through all 2.7 million rows, but yeah, okay. So let's just assume that that's worked.
Let's assume that that's done what it needs to do. All right, now the other thing is missing data. So sometimes records don't actually have a value for a particular column, and you've got to decide what you want to do with it. So you've got a few options. The simplest and most straightforward thing to do is to just ice the whole record.
So disregard
it. Every time you do that, you are removing data.
Yeah.
Data is valuable. Data helps you get a better model.
Mm-hmm.
And so you do stuff like that with caution.
Yeah.
However, no option is perfect, right? The other thing it could do is it could start biasing the data. There could be a reason why a record's missing.
Yeah.
And if you start removing records that have missing data, you might be removing a group of similar records that actually provides information about the data set and about the real world. And then all of a sudden you're becoming blind to that.
Yep.
So that's biasing your results, right?
Yeah. So I suppose there's a big question to ask when you're working with data in general. Why am I removing the record?
Correct. But that said, you can't actually run a machine learning model on missing records. So every alternative is less than perfect, right? Because the other alternatives are to fill those values. So you could fill those values with zeros.
Yeah.
But the problem is, what if you start adding zeros where zeros don't make any sense?
Yeah.
And so you could do things like add the mean value for that column, but all of a sudden now you're pulling the data towards the mean.
Yeah.
You can add the median, but that has similar implications. You could throw in a random number, but now you're adding more variance, right?
Or odd figures.
Yeah. So there are a whole bunch of different options. Some of the more sophisticated options are effectively to build mini models to actually predict what that value would be and fill that with a predicted value.
Okay. So it's kind of like
based on the information around it to try and say, well, this record is very similar to these records, so the likelihood is that the number is somewhere close to what it was for those similar records.
That sounds very complicated.
Yeah. So these are all your different options. I think we'll keep it simple here and just kill it, especially when there's only a small number of these records compared to the wider data set. You can do things like get rid of the records.
Yeah, because statistically it's irrelevant.
Well, maybe not irrelevant, but it's less likely to have an impact. And this is one of the things about machine learning is it's based on statistics, and in statistics there's no such thing as black and white. It's all about less likely and more possible. And so from a practicality point of view here, if you actually measure the number of missing records, it's not that many, and so we can potentially kill them, or we can put in an exchange value. So let's go, it's called clean missing data.
Yep, I see that over there. So I'm going to drag that and drop it in there.
Yep.
Just going to move these a bit closer together because I suspect we're going to run out of space. Okay. And then I'm going to...
So you just connect them up.
There, sweet.
So minimum missing value ratio, maximum missing value ratio, that just means what proportion is it willing to deal with. So cleaning mode, it turns out the columns, I'm sort of giving some stuff away here just to make it a bit quicker, but it turns out the columns with missing values are the delay and the arrival delay, depth delay and arrival delay.
Yeah.
So if you go launch column selector for that, select those two columns. Name.
Oh, there.
Oh, hang on, that's the different. You've got the wrong.
So I click the.
No, you don't. Oh, it's got all columns selected. Okay. Just click on launch column selector and just select the. You can go begin with no column or remove any of the others.
So what I'll do is I'll just move them all across.
And it's depth delay and arrival delay. The two that
depth delay and arrival.
So you normally have to do a bit of an analysis of your data, have a look.
Figure out what. So okay. So just those two.
Yeah.
And hit OK.
And then just let's go. Let's replace them with zeros in this case here. Depth delay.
What is replace using mice?
Mice is one of those inference things I was talking about. So it stands for multiple something equations, and it's about figuring out predicting values.
Yeah. Okay. So I'll just so we're going to do a replacement value of 0.
Yep. So in these cases here, we're just saying where it's missing, we're expecting the reason it's missing maybe is because the database drops zeros, or the particular person who's reporting it puts a dash in or something like that, right? So that's the sort of stuff you've got to dig through your data to find. Cool. So if you go back to the visualization of the data again.
After removing duplicates?
Yep. Either of those at the moment's fine.
Oh, that's right. They were the same data.
So this is the stuff about knowing what the data says and all that sort of stuff. If you look at one of the columns there is cancelled, one of the features is flight was cancelled.
Yep.
So a cancelled flight probably is not really useful to us if you think about it. There's not that many of them. But it's probably not that useful to us if you think about it, because we know if a flight's cancelled, it's not even going to arrive, right?
Yeah.
It's being cancelled. So we should get rid of any data in our set that relates to cancelled flights. So that's sort of the next step here is we want to remove any flights that have been cancelled.
Apply filter.
Yeah, let's see if that's the one.
And
anything else?
Now, why does this have two nodes after clean missing data?
Okay, so there's one usually in this. If you're not sure, it's the one on the left. It's usually the one that sort of flows through. The one on the right is the transformation. There's an action that's performed when you do something like that, right? And it has an algorithm associated with it. It can be very simple, but it can be like a logical thing or whatever. Yeah, but it's an action based on state. When we actually run a prediction, we can provide a whole set of flight data and say, give me the predictions on that flight data, or we can provide individual data about an individual flights in real time. So you can do batches of data, or you can do real time one by one. Either way, you've got to do the same things, the same cleaning operations on the new data that's coming in to provide predictions that you've done on the data to set up the models. So if there's missing data if we now build a model and we say, hey, this can predict flight flows, and we provide a whole bunch of information about upcoming flights, and we say we want to see if any of these will be delayed.
Yeah.
If that data that we're providing to the model has any of the imperfections in it that we needed to do to clean up the model, we need to apply the same cleaning operations to that new data before we actually run them through the model.
Yep. Okay.
Those are the transformations. So you can actually save those transformations so that you can apply them to the new data. You don't need to do that here. Sometimes, in this case, we probably won't get to that point just yet. And also, when you actually turn it into a predictive model, one of the cool things about this particular service is you can actually get it to create a web service.
Yeah.
And it does all that and handles that
for
for you.
Cool.
So you don't need, but if you wanted to extract it for whatever reason, it gives you that option.
Yeah.
Okay, let's do it with the script.
So I'm gonna delete that.
So we're gonna do a little bit of R. I'm trying to avoid this, but let's just do it. Our language modules.
Yep, over there. And right.
Execute R script.
Execute R script. Logo. Right.
So it's the top. It's the left one.
Yep, and that goes there.
Yeah. So you can provide. So the other ones are you can actually mix two data sets together. So that's what the middle one is for another data set.
Yep. Okay.
And the one on the right is actually to load packages if you wanted to load.
Yeah.
All right. So if you go to the top right now, you can see there's the code there. That one there.
Yeah. Okay.
So we don't need data set 2, so you can comment that out or delete it.
Cursor. Get rid of that.
Yep. You don't need any of that contents of the zip for it because that's the loading packages or whatever. So that's fine. So under the sample operation, that's where we're going to put executable code. So you can change the name of the output, whatever you want it to be. R works with one of the things you can work with in R are what are called data frames. They're just tables.
Okay.
Just like the stuff we've been visualizing.
Yep.
That's a data frame. R called that a data frame.
Okay.
What we're going to do is we're going to apply an operation where we filter out any cancelled flights.
Right.
So the output there, data set.
So I'm going to have data.set equals and then.
Yeah. So if you want to call the output data.set, that's the output.
What? I mean, could I call it data.anything or?
Yeah. Or you could just call it out, or you can give it any name you want.
Like that?
Yep.
Or does it have to say data.
It doesn't have to say data.
Yeah. Okay. And then I'm going to do what?
So we're going to apply an R function now. So maybe it's easy, so I just type it and explain what it is. But,
yeah.
So this is the data frame.
Right.
And we're going to take the column of it. So data frames column cancelled.
So dollar is within that data set, there's a column
called cancelled.
Yeah.
Wherever that is not equal to 1, so wherever it hasn't been cancelled,
Yeah.
keep those rows.
So basically that syntax says execute that operation, right? And assign the results to a variable called out.
Correct. So the double character arrow is a left assignment in R. The interior of the square brackets is take the data set 1, which is the input, and find the column cancelled, and then find where it's not equal to 1. So effectively drop the ones where it is equal to 1.
Yeah.
That'll give you a vector of trues and falses.
Yep.
Well, so you don't drop them, sorry. It'll give you a vector of trues and falses.
Yep.
Where that condition is met, you'll get trues. Where it's not met, where the flood's been cancelled, you get falses. That then becomes an indexing operator for the rows of the data frame. Okay. So wherever it's trues, those rows will be selected. Wherever it's falses, those rows won't be selected.
Yep.
This, after the comma, is which columns to take. So by leaving it blank, it means take all columns. So effectively what we're saying here is wherever that condition is met, whichever row that condition is met,
so wherever a flag's not cancelled,
take those rows, and keep all columns from the data frame. So you could choose to select only a subset of the columns, but we're taking all columns. And then from that, the square brackets are the indexing of that data frame, and then assign the results to a new variable, data frame called out.
Okay, sounds really straightforward.
We don't need to plot anything, so we'll remove that.
Yeah.
And then this part here is select the data frame to be assigned to the output. This is part of the Azure ML Studio assignment, but basically this is a mapping to the output port, whatever variable is provided to it.
Right. So will that all be changed to up? Okay, so it's saying, okay, so it's, so what does that sending output to the data set port actually mean? So is that basically assigning it to that node at the bottom of the square? If I
correct. So this first line here and this last line here are actually effectively, this might be a bad terminology, but effectively API calls to the Machine Learning Studio.
Yeah.
And so this first line here is get the data in and put it into a variable that we can now use in the rest of the R script. And this last line here tells us which variable to push to the output.
With you. Okay. Now I've got to move. And then just hit
tick. Okay, let's try executing that now to see where we're at.
So I would hit run all of it?
Yeah. It's pretty good at figuring out what it's already done and doesn't need to redo. So it won't do the remove duplicate rows again, for example.
I really like that this is such a visual exercise.
It's really good to get started. It's a bit clunky and slow if you're building anything large, and there's a whole bunch of issues around version controlling something like that.
Yep.
The really neat thing I like about it too is once you've got it, you can just click a button and deploy it as a web service, and that's a free thing that you can do. And you can just hit up that endpoint with some data, and it'll give you.
So you just send some data in, and it will spit back the results.
As long as you hook it up. And then the really cool thing is there's a Excel add-in where you give it that endpoint, and it actually, and then you give it the data, and you select it and run that add-in, and it pushes to the endpoint, and then prints the result back to Excel.
That's really cool.
So that's super neat. You could effectively get an Excel front end to this very, very quickly.
Yeah. Okay.
There you go.
So lots of green ticks equals lots of goodness.
Yeah. So if you look at the bottom left port now, that's the one that was there. That should have had those operations applied to it. The device output is where you actually see what is printed to the console by R, and it's where if you draw any plots or anything, you can see them there too.
Yeah. Okay. So if I have a look at this result set, there should be less than 2,700,000 and yep. Okay. So we've got 2,600,000 and something.
And we should have. You'll see that every value is 0. There's no other values. that feature now has no information in it,
Yes.
right? So you can drop that feature. We could have done that in the R script, but we can also do it now.
Does it matter though? I mean, so if we have a bunch of features that don't need to be considered as part of the overall prediction, does it hurt to just leave it in there as part of your data set, or do you have to strip it down to just the columns you need?
Yes, you need to strip it down to just the columns you need.
Pretty sure I don't have it.
There are some algorithms that will complain with a column that has effectively no information in it.
Okay. Right. For our purposes here, though, is it worthwhile stripping it out?
Yes.
Yeah. Okay.
Sorry. What's it called? Select columns, I think it's called.
Oh,
or select features.
Okay.
Select columns in dataset.
Do we select columns in dataset? Yep. And that'll go somewhere there.
Yep.
And then I'll take the result dataset and drag it into there.
Yep. And then you can go launch column selector.
Yep.
So you can now go with rules. This is
rules.
So you could select them individually, but you could go begin with all columns.
So
this is just another way to drive this tool, right? In the end, it's just about selecting columns. But if you go begin with all columns,
it doesn't have a. So I've got to go no.
And then go exclude.
Exclude.
So drop down to include.
Column names.
Column names, and we want cancel. Okay. And then tick that.
So
that's effectively reads as take all columns except for that column.
Yeah. Right.
Now, let's have a quick think too. You could also drop columns like the Boolean value, did it arrive late? In fact, we probably should, if you think about it, because so AR,
so that would be part of
delay 15. Yep, that one there. Right, and the reason I'm suggesting we drop that one is that tells you whether a flight was more than 15 minutes late. But if we're making a prediction on how late a flight is going to be, we're unlikely to already have that information.
Yeah, okay.
See what I mean?
Yeah.
Because if you knew whether it was 15 minutes late or not,
yeah,
you probably wouldn't need to make the prediction. Now, don't get me wrong, if you were told, hey, this flight is going to be 15 minutes late or not, that would give you a lot of information around predicting it.
Yeah.
But let's play, this is where you start thinking about the problem you're trying to solve and the circumstances in which it'll be used. In a real world circumstance where this would actually be useful, you probably wouldn't be privy to that information. So the model shouldn't use that information in building itself because it won't be given that information when it's trying to make a prediction.
For sure.
Is there any others there that we want to drop?
Probably that one too, departure delay.
Now that's an interesting one. You've got the departure delay, and we'll talk about that one in a second. And it comes down to the model that you're trying to build. So are we trying to build a model that predicts if a flight will be late after the plane is actually taken off, or is it going to predict it for the set of flights coming in the next day and we don't have any information about if the flight has departed late or not?
Probably before it's even taken off.
In that case, then you drop both departure delay and depth delay 15.
Yeah, okay.
Now, you also drop the depth delay if that's okay.
Yeah, I've got that.
No, that's the Boolean if it's a bit more than 15 minutes late. There's another one there that's the actual number.
Oh, yeah, okay.
Now, in the ones that I've done before, it's been after the flight's taken off making a prediction, and it turns out that how late a flight departs is like the biggest predictor of whether it will arrive late or not. Big surprise, right? So you're actually now dropping the most valuable feature of the model, but it is also not useful if the question you're solving is for the set of flights that are coming in the next day.
Which ones are likely to be delayed?
Yeah.
Okay.
So it comes down to the problem you're trying to solve.
Yeah.
Right? Everything comes down to the problem you're trying to solve. Cool.
Okay. So we hit tick. And you have to run that.
If you want to see the output, yeah. It's and this is the iterative thing. Like it's always handy, but it takes time.
Yeah, because I mean, you'll see that it's kind of broken something along the way.
Now, what we haven't done is any real data exploration.
What does that mean?
We haven't looked at the data visually and combed through the data to look for missing values. I've kind of given you the answers just to expedite the process a little bit.
Yeah.
But what you normally do is you'd be drawing graphs and trying to figure out which features are likely to give you the best results.
Okay.
You might be doing things called something called feature engineering, which is like trying to change features to make them more useful. An example being the day of the week feature there, right? Maybe to be useful, instead of having, and I'm spitballing, but these are the sorts of questions to explore. Maybe it'd be useful instead of going Monday, Tuesday, Wednesday, Friday, Saturday, Sunday, maybe it'd be useful going weekends and weekdays instead, right? We've also got the times of when the flights depart and things like that. Maybe it will be, and when they're scheduled to arrive. Maybe a useful feature is how long is the flight in the air for. So you'd actually figure out a flight time feature based on when it departed and when it arrived, and knowing time zones and all that sort of stuff. You could potentially build out more. You could effectively get more information, and information's already there, right? Because you're pulling it in, but the machine learning model might not recognize it, because in the end it just takes a matrix and churns the numbers. So you might actually want to make that matrix more meaningful. I guess is what I'm saying.
Makes sense. Okay.
All sorts of stuff like that, and that's what when they refer to feature engineering, that's what they're talking about: making new features and extracting little bits of information from those features. Okay. Dropping things, adding things in. Yeah. The other thing you often do is you want to explore which features are most likely to be predictive of your output. So you often do things like draw graphs of one feature versus another. Okay. So maybe we'll do that. If you grab, there's one called, just search for CSV. Yeah, just add it on there. Let's see if it's works. Okay, so we're going to drag that from there. I was originally going to do it in Excel, but let's try to be a little bit more interesting.
To there?
Yep. Hit run.
Hit run.
If you go to the output of the CSV,
so click there and then
go open in new notebook. And we're going to use Arc, that's the one I know better. So these are Jupyter notebooks. I don't know if you've ever heard of them before.
Jupyter notebook?
Jupyter. They allow for interactive coding effectively. And inline visualization, and you can actually put not markdown so much but you can add descriptive text, so you can actually mix your code with descriptions, and you can end up with this sort of interactive notebook. So if you hit, we're in that first cell up here, right? So the way it works is you write your code in these cells, and then if you hit this run, it executes the cells. Oh, that's great. It's broken. What it's meant to do is actually load the data into an environment. Let's move that to the side. Come back to that. Let's be really crude, right? Like just the sake of time and actually punch out a model. But we can then talk about things we can do to make that model better. Okay. And then come back to it maybe in the future.
Okay, sounds good.
So what you want to do is you actually want to split your data set into two. So there's a block called split data or something like that.
Oh yeah, I saw something along those lines somewhere. Split data.
That's it. Drag that. There, yep, that's it. Okay, so what you're going to do is we're going to take two sets of data, and when you do machine learning, this is a common approach. You take data to train the model, so it's called training data, and that's the one that your model improves itself on. So what you do, building a model is actually just an optimization process, right? So you have an algorithm, and your model takes a random guess at what the best fit is to produce that result. And then checks how good that guess is, and then improves it. And it's just this optimized this iterative optimization process where it converges on the best fit solution.
So it doesn't actually determine whether it's the best fit before it populates the value. It goes with its best guess and then reanalyzes all of it to see whether it fits in with the data pattern,
Correct.
if I could call it that, and then says, nah, that doesn't make sense. I'm going to try something else.
Correct.
Yeah, okay.
So it's actually an iterative optimization process, and you can talk about gradient descents and all the particular optimization processes. Doesn't really matter. What it is it starts with a guess, and then it just keeps improving that guess over time until it converges to a solution.
Yeah.
And convergence just means my next update is no better than my previous update by a certain tolerance. So once if you can think about it, it'll rapidly improve and then it'll plateau off. And once that plateau gets flat enough, once it's no longer seeing much improvement, it'll just stop iterating.
Yeah. And it'll say that's as good as
that's as good as we can get.
Yeah.
So that's the training data is used to actually tune that optimization and get the model as good as possible. Right?
Yep.
But you've now built a model on that data, so it's unfair to actually test the model against the same data because it's the best it can be for that data, right?
Yeah. Okay.
What you now want to do is you want to hit that model with data it's never seen before and see how good the model is.
Okay.
So that's what we're doing here. So we're splitting the data into training data and testing data.
Yep.
Okay. And you can choose the ratio of that split. The default here is half. That's probably a little, but the more you have in the test, the more robust your model is going to be because you're testing it against more stuff it hasn't seen.
Mm-hmm.
But the less accurate your model is going to be because it doesn't have as much data to actually work with when training.
So that's giving it about 1.3 million rows, roughly.
Yeah. So normally you see things in the vicinity of 70-30 splits or 80-20 splits.
So 70% would be for training your model, and then 30% would be to test your model.
Correct.
Okay.
So let's go with 70-30. That's usually what they give in examples.
So that's 0.7.
But there are no hard and fast rules here. This is where you sort of look at what you've got. Sometimes the less data you have, the less liberal you can be with testing data, and you might need to use as much as you can for training.
So is the first node 70%? The
Correct.
second node is the 30%.
Correct. There are different ways of splitting too. So this one here is a not a stratified split. It's a splitting rate. So this is a fully random split. So it's just randomly selecting rows.
Yeah.
Sometimes you need to be a little bit more careful about how you select rows and how you select data for the different sets. Especially if you've got ratios of like a classification and your data's been ordered in a particular pattern, you could actually select biased data and biased data to select. So you might need to be more careful about how you actually select things. You might want to preserve the distribution of your data. So if your data has a particular distribution, you might want to make sure the two samples have very close to the same distribution.
Yeah.
Stuff like that.
Okay.
Random's good. If you have enough data, and this 2 million's pretty big, the more data you have, the less problems you tend to have. And that's why more data tends to be good, is because all the errors and stuff you stuff up along the way kind of just comes out in the wash because you've just got so much.
Yeah.
Whereas the less data you have, the more careful you've got to be about using that effectively.
Sure. Okay.
Cool. Now we'll put in, this is not going to be a great model, by the way, because it's what we're doing. But the next thing you want to do is normalize. So let's pick normalized data.
There's something called normalize?
Yeah.
Right. So normalized data. Okay.
Yep. So drop that in, and we'll normalize the normalize before the split. Sorry.
Okay. So how do
you can delete the join.
How do I delete the join?
You got it selected and just hit delete.
Ah, there you go. Okay, so we'll move that somewhere there. We'll move that up there, and then
so one of the other considerations in your data is the units that the data is measured in. So if I measure the distance, how tall you are in meters, I'll get 7.9.
Yeah.
Right. If I measure in centimeters, I get 179. If I measure in millimeters, I'll get 1,000. Yeah. Right. The issue there is the machine learning model doesn't actually see the units; it just sees the numbers.
Yeah.
And then if I take your weight and I measure it in tons, I'll get a really small number. And if I measure it in your height in millimeters, I'll get a really big number.
Yeah.
And they're not on a similar scale. And a lot of algorithms will get confused by that and go, well, the big numbers are more important.
Yeah.
And give undue credit to those just because of the units we've measured it in.
So you want to create like standardized units.
Correct, and that's what normalizing is. So
Okay.
normalizing is about trying to bring everything onto a roughly standard scale.
Yeah.
And there are a number of different ways of doing that. You can take the maximum and minimum, make the minimum 0, maximum 1, and everything as a fraction in between.
Yeah. Okay.
You can do things like make the mean 0 and the standard deviation 1.
Negative or positive, yeah. Okay.
Stuff like that.
Yeah.
So let's just do something really simple here and just do the first one I said, which is the max-min normalization.
Right, so I'm going to click on that, and then I'm going to say max, and that's a 0 to 1, right?
Yeah.
Okay.
So all it does is it takes the minimum, makes that 0, the maximum 1, and everything else on the scale in between.
Yeah, okay. So do I have to do a column selector?
Correct.
And I'm going to go by name. And let's
Certain column 0 doesn't make sense, right?
We'll move all of those.
So year doesn't make sense, right? Year is more a label than it is a number.
Okay, yep.
It's an ordinal label.
The same with month.
Correct.
Day of months would be the same.
Correct.
Day of week would be the same. Carrier would be origin, airport ID. Those would kind of just be unique IDs.
Yeah.
Time, I could see it as being
you can make arguments there, yeah. And this is where you start to have to think about your data and what you're going to do with it.
Yeah.
Yeah, you can make arguments there. To be honest, we probably should have treated time a little bit better, but we're just being a little bit quick with how we're doing it. The arrival delay, definitely.
So let's leave time for now.
Yeah.
And let's just work on the arrival delay. Does that make sense?
Yep.
Okay.
So what we'll also want to do, I just realized too, is tick that. We're actually going to need to stick another one in before the normalized data. So delete the actually no, we can. We can keep it up.
Okay.
We can keep it up. We need to tell it things like day of the week, which has been assigned a number, doesn't actually mean a number. It means a label. Do you know what I mean? So 1 is actually an enum.
Yeah.
We need to tell it that.
Yeah. Right.
So edit metadata.
Okay. Would that go after normalized data?
Yeah, it can go before or after.
Oh, so we've already got the connector, so it's just there. Okay.
So some operations can be transposed and it doesn't change.
So we've normalized. So we said. So in that normalized data, we've taken arrival. What was it called? Arrival delay, and we said take the extremes, convert 1 into 0, 1 into the other into a 1, and then everything else converted to a fraction of, or something that falls in between that.
Yeah, although we shouldn't have done it on the label. I just realized. Yes. Normally that's correct. I just realized that it's not going to work in this particular circumstance. Yeah. When you're doing it on the label, there are a few schools of thought on what you should do. In this case here, so the label's the thing you're trying to predict. In this case here, it's going to cause us problems because, well, it's not going to cause us problems. We could come up with an answer, right? But our answer is now going to be a number between 0 and 1 that we're going to then have to reconvert back.
And we're not going to, it's going to be a pain in the ass.
It's going to be a pain in the ass. There are some algorithms where that's a good idea, others where it's not.
Okay.
The label is often a special case where you've got to think a little bit more about it.
So just to clarify what a label is, because you use that term a few times.
I've used jargon.
No, that's okay. So a label is something that we're trying to predict.
Correct.
Is that it?
Yeah.
Okay.
It's the variable that we're trying to predict, and specifically speaking, it's the variable that we're trying to predict in data that has been labeled, data where we actually know from history what that value was.
Yeah. Okay. So should I drop that whole normalized block?
Yeah, I think in this case, yes.
Okay.
Now, normally you need it there, but just thinking about the data set that we've got and how we've treated it's not going to be there at the moment.
And I mean, I suppose part of this exercise is recognizing that this is sample data, and a lot of the information in there has already been, cleansed and altered.
Part of the problem with an artificial problem is the artificiality of it.
Yeah, but it's a good starting point. Right?
Correct. Yeah.
Okay. Right.
So connect the edit metadata in. Launch the column selector.
Column selector. Yeah.
So this one here, let's go with the things we're going to make.
So what is edit metadata?
In this context, this is not necessarily a machine learning language, but in this particular tool, it's talking about the properties attached to the columns rather than the values of the data in those columns itself. So what is the type of data?
Oh, yeah, okay.
Is it an integer? Is it a string? Is it a categorical variable?
Yeah, makes sense. Okay.
So let's go with ones that we know are categorical variables. So for example, day of the week is a categorical variable. What else do you reckon is a categorical variable? See, when I say categorical, do you know what I mean?
Yeah, it's kind of got a specific value that is representative of something else.
If it's a number, it's an enum. If it's a string, it's you know there might actually only be 10 different values that it can take.
Yeah, like months.
Yeah, so months is probably a good one as well.
Day of month?
Day of month is an interesting one. It might not actually have that much predictive power. Like, do you think that the 21st day of each month is likely to have a recurring pattern on whether
who knows?
Yeah. So, and that's where you do some data exploration to find out. Maybe there is some hidden information there, maybe not. Maybe days later in the month, for whatever reason, tend to have more flight delays. That's where you actually start visualizing data.
So I suppose when you start looking at that, like immediately when you say that, I start thinking about, oh, shouldn't this be something our model does anyway? But that's not the question we're trying to address. The question is, which flights are likely to be early or late, right? Not what time of the month is a flight likely to be early or late.
Yeah. Machine learning models aren't particularly magic.
Yeah.
You kind of need to package stuff up to them and then ask them to run.
So it's very specific about the question you ask.
Yeah.
And there's no inference in it. Like, oh yeah, I know you asked this, but I've also discovered that on the 21st of September every year, flights are late.
Yeah, sort of. Sometimes you can run it backwards and you can actually, so what we can do is we can build a model and we can throw all the data at it. It's potentially an expensive way to go. And then you can ask it to try and figure out which variables are actually having the most impact on the model. But it will be better the more information you give it to begin with. So the closer you get it to being right when you start, this is the iterative process again. You could actually build a model and then tune that model. You not only tune the model in optimization, but you can actually then go back and say, how can I improve that model?
Yeah.
And one of the things you can do is try to figure out which variables, which features, which columns are actually having the most influence on the output, and make sure you value those more highly. And any ones that seem to just be noise, you can start dropping them.
Yeah.
And you can get a better model that way.
Okay.
The other thing that we very, very briefly touch on, and it's more advanced than what we're doing here, is you can start looking at machine learning models that build machine learning models.
Yeah, okay.
That's the area of research where you can start doing things like that, where it's a bit more just give it the data, and the first step it sort of does is, or the outer model is actually exploring which values are better to produce to make the inner model work, and that's. So
here we come.
Yeah, exactly.
Yeah, okay.
And then deep learning, which is the more neural network approaches and all that sort of stuff, can be a little bit better at sorting these things out. But, yeah.
Right, so I'm just keeping those two values in there. Is that it?
Is there any others? IDs are good candidates for categorical variables because they don't actually mean a number. They're a representation of a specific thing.
Okay.
ID1 and ID2. ID2 is not necessarily bigger than ID1.
Yeah, okay.
Carrier. Yeah, let's go with that.
Right on.
So if you go over to data type, you can just leave that unchanged, but categorical.
Make categorical.
There you go. And you can do things like change the names of the fields and all sorts of stuff, but we'll just leave it there for now.
Yeah, so I'm trying to understand what exactly is happening in edit metadata, and that's possibly a good space to end for this hour. Yeah. So we have this data, we've filtered out cancelled flights, the cancel column. We're then feeding this into the edit metadata, and we're saying those columns that we selected. So the airport IDs, I think it was, and carrier, we've marked those as make categorical. What is it actually doing though?
So what that means is when it hits the machine learning model, it's not going to say that airport ID 100 is twice as big as airport ID 50.
Right.
You know what I mean? Because that doesn't make any sense. Okay. Because airport ID 100 actually in real terms translates to Florida International, and airport ID 50 translates to JFK, right?
Okay.
And Florida International is not twice as big as JFK for the purposes of understanding the model. Mm-hmm. So what it does is it forces the machine learning model to recognize that these values are labels.
Are literals? Is that kind of...
I don't know what that means.
So if you have to think of like a string literal in traditional programming, right? It's like, hey, there's this string of text. It could be interpreted as something, but it's not. Take it for granted as it is. Don't make any inferences on what it could be.
Yes.
Right? We're telling you categorically
yes.
that this is what it is.
Yes.
Don't try and figure stuff out with it.
Yes. That's a good analogy.
Yeah. Okay.
Otherwise, it would do things like, if you think of a number line, it would start placing them on the number line, and then shifting them around based on that. In this case here, it's going to treat them as,
values that identify the record.
Correct.
Yeah.
Not as one thing is twice as big. Yeah. There is no numerical relationship between the values in this column. Whereas something like arrival delay has a numerical relationship.
Yeah. Greater than, less than. There can be inferences made from it.
And even bigger than greater than and less than, a flight that arrives 10 minutes late is twice as late as a flight that arrives 5 minutes late. So you can actually do numerical algebra on it.
Yeah. Okay. And the purpose and the reason we're doing that is to kind of prepare for later stages when we're actually running through the model and we're trying to infer those predictions.
Yes.
We're telling the model, okay, you don't need to worry about this stuff.
It needs to worry about that stuff because there is information encoded in those variables, but it will treat categorical variables different from numerical variables. Okay. So numerical variables, it can start doing things like, if I see a number that's 3 times as big as another number, that can imply 3 times more weight on this variable. But if I see ID 1 and ID 2, I'm going to treat them as effectively, in reality, a lot of models, yes, no labels. Is this ID 1 or is this ID 2?
Okay. Yeah, sweet. Okay, so the next session we'll pick up from that point.
Yep.
And what comes after this?
Very, very quickly, we split the data.
Yeah.
We build the model on the trained data, and we test it on the test data.
Yeah. Okay.
And then you go, how good's my model? And you go back and try and improve it.
Yeah. Okay. Cool. So
we're actually really close to building a model. But we'll do that next session, and we'll then also evaluate it, and then talk about how we can improve it, and then we can go from there and maybe do something interesting.
Yeah. Okay.
But this is the main thing I was trying to show you here is the preparation of data and how important that is.
Yeah.
Because you'll see actually running a model and putting it in is like one box.
Okay.
Just connect it up.
Yeah. Okay. Yeah. So all the preparation is the hard work and figuring out what needs to be done